scale. That's fine. Not a theories. लाइव कर चल रहा है हाँ अवधि मिनट स्टार्ट करिए नॉट 9:43 okay it's 9:45 let's get started good morning how was your evening had fun did you go anybody do any sightseeing in Bhubaneswar no no okay were you guys able to finish that spreadsheet mostly okay we'll go over that in the tutorial so I did receive several of those homework 0 submissions but I will keep track before lunch submitted no lunch for you right we agreed to that one so today we're going to have a lot of stuff mostly on subgrade evaluation and we're going to focus on a lot of tests that you have heard of I think you have heard of all of them pretty much I don't know how much details you have gone into so we'll cover a lot of those stuff talk about CBR plate loading a little bit of VM stabilometer quite a bit of triaxial then we'll take a look at some other stuff as well falling weight deflectometer we'll see how much we get into get through because it's a lot of stuff we should be able to also talk about back calculation after today's session I don't think we'll have time to go over the full back calculation software we may do that in the tutorial maybe tomorrow because today is something related to triaxial we'll figure it out and then we're going to talk about some DCPs some expedited field tests and stuff like that okay this is the Menti link for today so scan this keep it open or keep it in your browsers we'll get to that I haven't launched anything yet but you're going to use that okay again I as I said yesterday this slide set is borrowed from a lot of people some of my contribution of other people's stuff that I have learned over the years my PhD advisor Errol Tutumler he's a very well known expert on transportation geotechniques so I borrowed a lot of stuff from him so acknowledgements we're going to talk about strength we're going to talk about why strength is important what properties or what behavior of a pavement is affected by strength we're going to talk about plate loading triaxial then we'll go into stiffness and we'll talk about modulus not really go into resilient modulus a lot but we'll go into modulus from plate loading so that's a very common thing that people do we are going to talk about what are the advantages what are the disadvantages for doing that then we are going to talk about some stress strain curves and stuff like that What are the properties that are of interest to us? We want to know strength, stiffness, then permanent deformation, which is basically your plastic deformation, which manifests itself as rutting, right? So we're going to talk about what affects rutting, how do you measure it, how do you quantify it, and day 3 and day 4 is going to be a lot more of repeat coding and stuff like that. Swell potential, frost action will just briefly mention, and then moisture sensitivity to strength and modulus, will go over that quite a bit, how moisture affects these things and stuff. Okay, before we go, I want to do a very small exercise on compaction, and this is something that you all said relatively comfortable doing this, right? So how many of you have done lab compaction tests on soils, aggregates, anything? Okay, what's the test called? Proctor test. And what, there are two variations, right? Standard and modified. Who remembers the ASTM numbers? You remember IS numbers? Okay, fair enough. So it's from what I have gathered is that IS is basically based on ASTM directly. So I don't remember the IS numbers because I don't work with those, but it's ASTM 698, D698 and D1557, okay, those are the two numbers. So I have a little exercise for you. Here is the screenshot of the two titles, okay. Read the first title, somebody, I forgot your name, I'm sorry. Yeah, read the first one. 600 kilonewton per kilonewton meter per meter cube, right? What's missing? What's missing from this title? Proctor, right? What's the second one? Who's going to read the second one? Akshay, you want to read the second one? 2700 kilonewton meter per meter cube, right? Again, what is missing? Proctor. So here is news for you guys. The test methods that you follow are not Proctor methods. Okay, let me show you why. This is a trivia I do all the time, and that is the reason I do it is because this was first time highlighted to me during my PhD dissertation exam by Professor Marshall. Oh, by the way, did you guys read the paper yesterday? Marshall Thompson's paper? Okay, good. So, no, this is a modified one. You can't do that. I need this standard. Okay. The equipment and procedures are similar as those proposed by R.R. Proctor with this one major exception. His rammer blows were applied as 12-inch firm strokes instead of free fall, producing variable compactive effort depending on the operator, but probably in the range of this, and standard effort test is sometimes referred to as the Proctor test. So what I'm trying to say is when you do an engineering document, do not write it is a standard Proctor test, because you are not doing a standard Proctor test. Nobody is doing it, right? So Proctor, when he developed the test, he developed it for sandy soils, and it was firm blows. So what means is that you take the hammer, you actually bring it down, and you use your hand to do this. It was not a free fall. It is not just mgh as the energy. So there is a lot of variation in that. So it was actually modified into that. So that is the reason the tests should now be referred to as standard compactive effort or modified compactive effort. Do not say standard Proctor, modified Proctor. Colloquially, it's okay, like when you talk about with people, but in engineering reports, it's actually wrong. I mean, 90% of the people don't realize it, but that's how it is. So just a little trivia before we get started. All right. So we're now talking about pavement design, right? Or pavement, how are you going to do a pavement design, and you need to classify or quantify or or characterize your subgrade. So this is a NCHRP 382 that was done by Professor Anand Puppala pretty long back now, and synthesis reports, if anybody has read them, they are actually survey of state practices. It's not a research report, it's a practice report, it's a synthesis of practice, right? People said that, you know, procedure used for pavement design, some people were still using 1972 AASHTO, lot of people are 1993 AASHTO. MEPDG was only one agency, agency specific mechanistic procedures, and then no response and stuff like that. So what I'm trying to say, the numbers have probably changed. I mean, this exact survey probably has not been done over the last 10-15 years or something, so I don't know the exact results. If somebody did it, you can pull it up. But the idea is that a lot of people are still relying on the AASHTO 1993 or a version of it and stuff like that. Of course, the MEPDG number is now larger, but it's not as widespread as one would imagine. I mean, people would think that, oh, MEPDG, if the project finished in 2006 or something like that, 2006 or something. It's been about 15, 16 years or more than that, that then the MEPDG was developed. But implementation has still been challenging. A lot of people are still playing with it, but full-time implementation has not happened. Then there are other agencies. Corps of Engineers, they actually do, for flexible, they just do like a CBR based method, right? One of the main challenges of the Department of Defense is that when they are going to like a new military base or something, when they are establishing, they don't have 6 months to collect soil sample, wait for the results, do a detailed characterization. They need the information like yesterday, right? So that is the reason a lot of their work has to still be based on empirical or quick tests or something. They cannot do, you know, even a simple CBR test is a 96-hour soaking, right? It's a 4-day. That's a lot of time. You can't afford that, right? So a lot of quick tests and stuff. People do modulus of subgrade reaction. FAA or Federal Aviation Administration, they also did modulus of subgrade reaction, and then they actually have this LEDFA or far field. Now it's called far field now. I think that's the new one, current name, which is the analysis software and stuff. And AASHTO, of course, the ME design or MEPDG, will talk a little bit about that. So CBR, people were using 19 states. R value, how many of you have heard of R value before? No? Okay. How many of you have heard of the Weem stabilometer or stuff, something like that? Or do we cover Weem method of mixed design here in India? No, no. Only Marshall and Superpave and stuff. Okay. Okay. So we'll talk about it. The R value is a resistance value. Triaxial testing will go quite details, and we'll take a look at those. So 19 respondents use resilient modulus obtained from different methods other than laboratory and field measurement for subgrade and unbound basis respectively. What does that mean? So if you do an AASHTO, I know some of you don't have any pavement design background, so that's a little challenging to understand everything. But if you look at it, even if you go through your AASHTO 1993, subgrade modulus is an input, right? That is how it all starts. That's the support that you go to start and stuff. But how do you get the modulus? Where are you getting that from, right? A lot of times you'll hear a thing like 1500 CBR or something like that, or I think there is a 2555 CBR raised to the power 0.63 or something like that. There's another equation or something. But the whole idea is we are using something to predict something else, and what is the logic behind it, what is the accuracy behind it, how much error are we introducing, what is the tolerance level and stuff like that, right? So we need to be careful about. How to characterize structural support? Again, some people followed 1993 AASHTO, some people followed local correlation. Most of them, a higher number, actually did local correlations. Now, as I said yesterday, empirical methods, as long as they are applied in their own domain, may actually work. Now, whether you are doing it the right way or not, that's a different question. We'll get into that. So that's basically what it is. So now we're going to, so that's just the basics. Now we are going to go one step at a time into each test method, and we'll talk about it. Okay. How many of you have run CBR? Quite a large number. Good. Soaked or unsoaked? Soaked. 96 hours. Has anybody done unsoaked stuff? Okay, some of you. Okay, so we'll go into that. So those of you who have not, CBR is basically the oldest living dinosaur in the world of pavement engineering. Okay, it's a California bearing ratio test. California is because it came out of California. The person Porter, Jim Porter, I think is his name. He developed this. He was working for the California Highway Division, and then he basically said, found a magical aggregate. Okay, when I said magical, it's not, at that time it was perfectly fine. He found a well performing aggregate, and he said, this is my reference, right? What we are going to do is I'm going to run a test with a plunger. It's a metal plunger that is actually going into the soil or into the aggregate at a given, and I'm going to keep measuring the resistance that the plunger is experiencing, and I will pick it at two different values, 0.1 inch, which is 2.5 millimeter, and 0.2 inch, which is 5 millimeter, and at those values I'm going to measure the pressure, and I'm going to compare that with the pressure I experienced when I tested my magical aggregate, right? And that ratio is what is California bearing ratio is, right? The thing is, so this is a company called Gilson. They sell a lot of equipment. This is their website. I just got it, and then if you see, there is some CBR ranges that they report and stuff. This is like a schematic of the thing. Of course, there is no proving ring these days. You have load cells, right? You don't need a proving ring. You don't need a dial gauge. You have an LVDT. You just go and you measure and stuff. This is the specification, 1883. 3 square inches of area, which is 1.96 inches of diameter. You can convert that into millimeters, and then you have a 6-inch mold or a 4-inch mold or whatever, right? 6. So what you do is you have the crushed stone values. So at 0.1 penetration, the crushed stone had a 1000 psi resistance. At 0.2 penetration, it had a 1500 resistance. So that's the crushed stone. That is the magical aggregate I'm talking about. And then you test your own aggregate or soil, and then you take the ratio, like whatever your value is here, 125, you divide that by 1000. So your CBR is 12.5, right? There are two schools of thought. Some people say that it should always be referred to as a percentage. Some people don't refer to as a percentage. I'll let you do what you do, right? I usually write it as a percentage, but it's not a requirement. The mathematics is that you actually measure at both of them. If by any chance your 0.2 millimeter measurement is higher, then you actually report that. You don't go with the 0.1, right? So that's basically this. You use 2 greater than 1. So you do a 4-day soak, 3 square inches, and then it record, and then you compare the soil strength. Okay. So typical results, if you look at it, this is, because CBR is so old, these graphs, some of these graphs you are going to see are going to be very old. This is like the crushed rock, the reference that they had, and this is penetration, and you actually try to get, typical values for something. Some of the things I'm not very familiar with the Indian practice, but the point is, usually for a crushed rock you should get something at least 80 or something like that. That's a good number. A lot of times you get 100 or something, or even greater than 100. We'll get into those things. So what limitations somebody already did it? Was that launched already? Okay. All right. Associated with the CBR field, with the CBR test, it's not necessarily field. I'm talking about lab. I'm talking about CBR. Okay. So the person who has already done it, you can do it again. I have allowed multiple responses. So question is, what do you think are the limitations of CBR before I go into anything? Yes. Yeah, we'll get to that. We'll get to that. Okay. We have some good responses. Uh, let us go through some of them. If you have input, folks, please continue doing this. I'm starting to talk because I see we have so much material today. It's already 10:15, and at 11:15 we're supposed to have a break. In 1 hour, I don't know how much I can go. So we'll keep moving. I see some of them are practical concerns you all have, like for example, human error. Test takes a lot of time. There is it's difficult to run on clay soil and stuff like that. True. Okay, but I actually have a different question. So you have a steel plunger that is going into the soil, right? When was the last time you saw a steel plunger going into an actual pavement? No. It's a bearing capacity kind of a test, like a bearing. It's California bearing ratio. Everybody has taken geotech classes, I'm assuming foundation classes and stuff like that. So capacity is stuff like that. Do we design pavements for bearing capacity failure? No, we don't, right? Another thing, what's the diameter of the plunger? I said 1.96 inches, whatever that is, whatever that is, right? 50 millimeter probably, right? And what's the diameter of the mold? 150, right? So, and what's the depth? Do you remember? 127.3. That's 5 inches. No, isn't it closer to 4 inches? I think it's 101 or something, right? Closer to 100 maybe. I think. I don't remember. I haven't run this for a long time. Do you remember the concept of a slip surface? Like when you do a plunger or a bearing capacity, there has to be a slip surface that develops, right? You are inside a steel mold. What is the likelihood that actually a slip surface is developing? It's not. Your mold is severely affecting the development of a slip surface, right? How is your pavement loaded? How is your pavement loaded? When you it's my fault. My Mac is not on charge. I'll put it to charge. What kind of loading do you experience in a pavement? Who said cyclic? You're going to buy me lunch today. No cyclic. What did we say yesterday? Repeated, not cyclic, right? We don't load pavements in cyclic. Okay, so we have repeated loading of a tire, right? Of some kind of a rubber thing or whatever, right? Whereas you are trying to simulate that by taking a steel plunger and pushing it into a soil, right? And you are saying that we are going to get modulus out of this, because the mechanism is completely different, the loading phenomenon is completely different, right? So CBR is a good index test, and it is a good test when it was developed. When was that? 1930, 100 years ago, right? Here is the fun part. 1977 keynote address by Stephen Brown, okay, 50 years ago at Nottingham. He said Jim Porter, who as the soils engineer for the state of California introduced this, said in 1938 the bearing values are not a direct measure of supporting value of materials. In 1950 he said the results are influenced only to a minor degree by elastic deformation. Okay. In 1950 Turnbull said the CBR is an index of shearing strength, and we use it all the time to predict modulus, right? So the person who developed CBR said don't do it, but after World War II it was widely accepted, and that is the reason we are keeping doing it. Okay. Oh, by the way, I think Dr. Sahu probably said this already. At the end of the class, maybe on Friday or something, mostly we will give you all PDFs of all lectures and stuff, so it'll stay with you, so you'll have PDFs. So the point is a CBR, and then in Crony 1977, the shear strength of a soil is not a direct interest to the road engineer. The soil should operate at stress levels within the elastic range. Pavement engineer is therefore more concerned with elastic modulus of the soil and the behavior under repeated loading, not under monotonic punching kind of loading, right? That's not how you're going to predict modulus, but it is an index test. It does give you some stuff. Okay, it's not a fundamental property. It is not based on physics. Like you cannot do an equation for it. You cannot use a CBR directly in a constitutive relationship or something, right? It's not a fundamental property. Soaking. Who asked? You asked, right? No, you asked. What's your name? Ashish asked, what is the point of 96-hour soaking? Why do we do it? Who can answer that? Why do we soak it for 96 hours? Say it again. Saturation. Yes, yes. So water is the worst thing that can happen to your soil or aggregate, right? So you're basically soaking it to simulate, of course, 100% saturated, and simulate the worst possible moisture condition that that soil can have, and you're going to get a very, very, very conservative number. But the problem with the CBR by that method, and that is the reason I didn't answer your question at that point, is because we were going into this. In the field, how many times do you actually see the layer is completely flooded? It's not. I mean, sometimes it is, but then the water gets removed. How many times do you see the entire layer is at one moisture content which is 100% saturation? Never happens, right? So not uniform moisture condition in the field, it's not a realistic situation. Something wrong? Okay. Static punching assumes good CBR indicates good performance under repeated loading. Again, strength versus modulus, very different things, right? And if you want a reminder on that, how does that work? You have a stress versus strain curve, right? Epsilon sigma. This is your strength. This is your modulus, right? I can have a much lower modulus but a much higher strength. I can do. You can have it, right? So the question is, this and this are not always the same thing. You cannot, you should not be using it, right? So that's the limitation. Mold size, I told you already. Bearing capacity, you need the depth of 2 to 3 times phi just to develop a proper bearing capacity. If you go back to your Terzaghis bearing capacity failure and stuff like that, right? So that's the reason mold size affects it. Also, there is this is just a very trivial detail. I'm assuming whoever is running CBR, you have modern equipment that actually does the zero correction at the very beginning, because there is some seating that happens. It's just a little trivial thing. I'm not going to spend much time. It is very common practice to measure when you do a CBR test, you do it at multiple moisture contents, and then you actually report it just like you report a moisture density curve. Like you have a moisture density curve like that, and you actually correspondingly you report the CBR values here and stuff. And this is I think you probably also do swell testing on CBR as well, right? I have been primarily an aggregates person, so I have only like once or twice in my life. So I don't know a lot about swelling, swell tests and stuff. But the point is soaking. So this is one more thing I wanted to highlight to you, is a lot of agencies, when they realized the disadvantage of 100%, like 96 hours of soaking and stuff like that, they actually moved to what is known as unsoaked CBR. They prepare it, they test it at that moisture content, the molded moisture content. And as you can see, as the moisture is drier, the CBR is much higher. It doesn't follow the bell-shaped curve. Like if you see a typical CBR test should follow a typical moisture density kind of a shape. It's a bell. Whereas the value actually peaks a little bit on the left side of the OMC, because dry is better. We're talking shear strength, right? Drier is better, so it will peak on the left always. But the point is, for all practical purposes, this line is of a lot more interest to you, because in practice you do unsoaked CBR. I actually don't know of many agencies in the US who do actually soaked CBR. Unsoaked is a lot faster, and it gives you some value and stuff. So this is just another test result. This is a typical way of presenting. You do a density and the CBR on the second plot and stuff. And as I said, the CBR peaks on the left side of the OMC for a compaction and stuff. Typical results: when fines increase, CBR decreases, because it's a strength. Like if anything, it is a strength index, right? It gives you some kind of shear strength. I would be much more comfortable if you used CBR to predict shear strength than CBR to predict resilient modulus. It's a strength index for all practical purposes, right? What does CBR greater than 100 mean? Right? It's an arbitrary reference material that you chose, which is probably not available anymore, right? So what is greater than that mean? Like how do you compare that with respect to your mechanistic performance and stuff like that? It's still questionable, right? Compaction affects a lot. This ASTM D1557 is your modified, this is your standard, and again, in this short course, we are not going detailed into compaction because we kind of assume that you have a good background. You know that compaction is like MDD and OMC, these are not fundamental properties, right? They are dependent on the compactive effort. So a lot of times you change the compactive effort just to study. Like in study, this was another study by, I think, Professor Thompson. What he did is he developed an intermediate compaction. Like if modified is say 5 layers, if if standard is 3 layers, he just made a 4-layer sample. So that's intermediate compact, like somewhere in the middle and stuff. And as you can see, as moisture content increases, because it's a clay soil, CBR collapses really fast. So moisture is a really bad thing. That is the reason you soak, is because you are going to get the worst possible thing. But what is the point of soaking an aggregate if it is a very low fines aggregate? Because what happens to the water? It just drains, right? So your water does not really change the behavior as much unless you have plastic fines and stuff. So that's basically soil groups. Some people have A1, A2. I mean, they learn AASHTO classification as well, right? Most of them, yes. So this is AASHTO classification, not USCS, right? Unified Soil Classification System. AASHTO is the other one that was used in America. A1, A2, A3 is a granular. A5, A6, A7. These are the fine grained soils and stuff. But bottom line is, so IBR as actually is what Illinois came up with, is the Illinois bearing ratio, and then they just had ranges and stuff. But the bottom line to talk about is, for any soil classification, you have huge ranges. So if you just say that I have a CL, tell me what the CBR is, it's not possible. It has a lot of things that affect it, right? So it's not a fundamental property, so we should not be focusing on that primarily. Granular soils, if it is not much fines, then CBR is basically a function of density. The more you compact, the better they pack. On the other hand, I told you something yesterday is the challenges with open graded aggregates. And so I gave the example of glass marbles, right? No matter how much you compact, they're only going to get somewhere. And then if you do a CBR, it will look like really good crushed aggregate, but you will get CBR values of like 10, 15, because it's not stable. The matrix is not stable, right? So those are all does that mean the material is bad? No. You confine that material, it will take a jet plane. It will withstand a jet plane. So that's where we're going to get into the stress dependent behavior on day 4 and stuff, when we talk about why aggregates are great value when you actually confine them properly and stuff. Then you can load it as much as possible. Fines matrix, you can have no fines, just the right amount of fines, and greater amount of fines than optimum and stuff, right? Moisture content, certain point, if there is no fine, the water you add, what happens to it? It escapes. So your material or your sample does not really change behavior because the water is gone, right? So it's very important to realize where you have optimum fines or greater than optimum fines. Of course, optimum fines, because matrix is so stable, you have really good resistance and stuff. So that's what the example, again, if you go back to the railroad ballast example, the fouled versus unfouled, that's what I was talking about, right? If it's fouled ballast, if it is dry, it can actually be really good sometimes. The problem is when it rains. It collapses, right? You have a lot of correlations like this. You can have AASHTO correlations, ASTM, the USCS, basically the Federal Aviation Administration, the R value, modulus of subgrade reaction, bearing value and stuff. So CBR, you can actually have some ranges and stuff. But look at, let's take something like an ml, like look at the range of the ml here. So the CBR can go anywhere between 4 to 15 or something like that. So it's over, like, if you go into an A24, A25 soil, it's a 20 all the way to probably 80 and 90 and stuff. So it's a huge, huge variation. So it's not a fundamental property. It is not something that we should bet our money on and stuff. So it's just background. That was a quick overview of CBR, right? What are the challenges? Why you should? It's okay to test, but you need to take it with a grain of salt. You need to remember what's going on. What are you testing? What is it telling you? It's not something that, so that is the reason. That is the reason the 1500 CBR is something you can say that I have tested. So let's say there is an agency who is dealing with the district of Khordha or something, and they encounter 4 or 5 different types of soils. And over the years, they have tested the soils, they have characterized it, and they have developed a database or something saying that, okay, my CBR relationship is something about, resilient modulus at some kind of a stress state is about 2500 times CBR or something. That's okay, because they have done it for their soil. They know what is representative. We cannot use it widely. It's just not something you should be doing. Alternatives. The first one we're going to talk about is Weem stabilometer. Okay. So Weem stabilometer, if you ask me, it's actually not. So there is a gentleman called Weem. I think his name is HC Weem or RC Weem or something. I don't remember his exact name. He was again another engineer working in California. He came up with this mixed design methods for asphalt and stuff. So there is Marshall, there is actually Weem, and then there is Superpave, and now BMD and stuff like that, right? Weem actually developed something called a stabilometer, and I am actually a bigger fan of the Weem stabilometer than of CBR, because to me it's a lot more scientific than just punching a soil or something. The whole idea is it's related to Poisson's effect. What is Poisson's effect? Say again? That's Poisson's ratio. Minus epsilon 3 over epsilon 1. That's Poisson's ratio. What's Poisson's effect? Yeah, exactly. Something like that, right? I mean, I would not say x and y because I can always put x and y in the same direction, same plane. But yes, longitudinal axial compression will lead to radial expansion and stuff like that, right? So Weem stabilometer, what it does, it is basically measures the resistance to displacement is expressed as a function of the ratio of the transmitted lateral pressure to that of the applied vertical pressure. So when you apply a certain amount of vertical pressure, how much lateral pressure is being transmitted? When you have a balloon, when you squeeze it in one direction, it is going to expand in the other direction, right? Called Poisson's effect. So the stabilometer is actually based on Poisson's effect. So there is a little video here. We're going to play this.
You'll take the adjustable base out of the oven, place the stabilometer onto it. You're going to take a measurement from the bottom of that metal ring down to the top of the base. It should measure 3.5 inches.
This is also used for asphalt, by the way. So you'll see this one is actually for asphalt, but it's the same thing.
The oven temperature is always 60 C or 140 F. Okay, once you've taken that measurement, you're going to be taking the thick-walled cylinder out of the oven, called the follower, placing it into the stabilometer, and then you'll be turning the horizontal pressure up to 20 psi, and then you will allow it to stabilize. While it's stabilizing, it's heating the oil in the bladder. Once it has stopped moving, you're going to take the follower out, place it back in the oven, and get the thin-walled cylinder out, the calibration cylinder, place it into the stabilizer, turn the horizontal pressure to 100 psi, and once again allow it to stabilize. Simultaneously, you'll be adjusting the turns displacement dial to 0. So it takes a little time for it to all stabilize. When you're done, you want the horizontal pressure at 100 and the turns displacement dial at 0. Once you have both of those dials set, you're going to be turning the horizontal pressure handle out exactly 2 turns, watching the turns displacement dial.
So this is all related to calibration. You should not worry about that much. The initial part.
So if the needle is a little above the 5 psi, you're going to have to let air out. If it's below, you're going to have to let a little air in. So with the calibration cylinder still in place, with it set at 5 psi, you'll measure the exposed piston length, which needs to be 2.8 plus or minus 0.2, which tells you if there's enough oil in the bladder. So you'll be taking the calibration cylinder out then, and you'll be removing a specimen from the 140 oven, placing powder around the outside of your specimen, or you can actually put powder on the inside of the stabilizer bladder. Allow it to slide down into the stabilizer. If it doesn't slide down, turn the handle out till it easily slides down. Making sure it's in there firmly, and you're going to place a follower above it. Turn horizontal pressure to 5 psi. You're going to carry the stabilizer over to United compression machine. The proctor will lower the head after you've centered it underneath there. They're going to lower the head so it's just about touching the follower. Once they've completed that, then you're going to have to recheck and make sure that your horizontal pressure is still set at 5 psi. Once you've done that, then the proctor will start the test for you. They'll ask you what the rate is, which is 0.05 inches per minute. They'll ask you when you're going to take your first reading, which is at 5,000 pounds. You'll be able to watch on the computer screen when it gets close. You'll take your reading, which in this case is about 32. Write your reading down.
So this is all I wanted to show you. Oh, it switched. That's okay. This is all I wanted to show you. What did he do? They actually applied load from the top using the compression machine, and then they saw an increase in the pressure on the lateral reading. It was 5 or something, it went to 30 or something, right? Why did that happen? Is because of Poisson's effect, right? You squeezing, it's expanding laterally. The bladder is full of oil, and that is the reason it is experiencing, right? So if you want to calculate the R value, this is the equation. Okay, and what do you see here? Take a look at it. So think about it this way, folks. D2 is the displacement of the stabilometer corresponding from increasing horizontal pressure from 5 to 100 psi, right? So if it's a completely rigid material, to increase the pressure from 5 to 100, how much will be the displacement? Theoretically, full rigid. So what is the displacement? 0. So D2 is 0. So go to that equation. D2 is in the denominator, so that becomes 0. So that term basically becomes infinity, right? I mean, don't go into calculus into me, but yeah, that's infinity, right? So 100 divided by infinity becomes 0. So 100 minus 0 becomes 100. So R value is 100 when it is 100% rigid, right? On the other hand, if it is water, what is going to happen? When you increase V, pressure in the vertical direction, how much will be the increase in horizontal direction? same pressure, hydrostatic, right? So PV over PH becomes 1, 1 minus 1 becomes 0 plus 1 becomes 100 divided by 1 becomes 100, 100 minus 100 becomes 0. So water is 0. So these are the two extremes, and then you are somewhere in the middle when you are testing your soil, right? So that is the reason, because I find it much more scientific than just plunging a CBR and trying to compare it with an aggregate or something, right? So, but again, it's still an index test. It is not, it doesn't give you constitutive values or something, but at least the index is based on Poisson's effects and stuff like that, which is what I like, right? So that's what R value is. That is something that used to be tested in the past. So Idaho, where I was before I moved to Oklahoma, they still used R because they're near the west coast and stuff. California, they still have a huge database of R values. The state of Washington, where Seattle is, they have an R value database and stuff like that. Some of them are slowly moving away, like Idaho is moving away from it, but they still have, the older engineers will be able to really tell you that, oh, this is an R value of this is an R value of this, and stuff like that. Okay, so we cover 2, CBR, stabilometer. Now go to plate load test. Honestly, you all probably have seen more plate load testing than I have, because India, I know that there is a lot of plate load testing that happens, right? In US also it happens, or in airfields and stuff, in army installations or military. I haven't seen as many in my life. I've seen, I think, only 5 or so. So it's a static loading test. It assumes what is known as dense liquid foundation or Winkler foundation. Does anybody know the definition of a Winkler foundation? Question? Yes, yes, but what is the main property of those springs? Yes, one keyword. Well, no, that's not that's under a slab. That's different. That's not Winkler foundation though. You are on the right track. You're just missing one keyword. The deformation at any point depends on the load at that point only. There is no shear transfer of the deformation happening. Like, so what I'm trying to say is, there is a spring here, there is a spring here. If this spring deforms, does not mean this one will deform. It's only dependent on one point. That's basically what it is, right? This is we talked about this yesterday. So it's pressure is equal to K multiplied by deflection. So the unit is PSI per inch, or PCI, pounds per cubic inch, or something like that, right? Or Newton per millimeter cube or something, right? It's conducted to measure subgrade soil input parameter for concrete pavement and slab thickness design. This is another little video that actually will show you. This is by Tensar, actually gives a good input for that.
Hello, and welcome to this first episode of Tensar Ground Coffee. A few minutes on ground engineering to enjoy while having your coffee. So in each episode, we're going to cover a snippet of ground engineering that is usually somehow related to Tensar applications. Now, just recently, we've been doing quite a few tests on
Volume
platforms for piling rigs constructed out of our mechanically stable.
Let me see if I can change the audio source to the room because I'm connected to HDMI. I don't know if that's possible. Is there a speaker in this room? I connected it to the other one. I don't know where the volume is. Huh? It should. It is not. No. No, yeah, no. That's it. Sub maximum. No, the volume, previously the volume was coming through my laptop right here. This was
On working platforms
here.
for piling rigs constructed out of a
No, it's still here. Not the room.
Hello, welcome to this first episode of Tensile Ground Coffee. A few minutes on ground engineering to enjoy while having your coffee. So in each episode, we're going to cover a snippet of ground engineering that is usually somehow related to tensile applications. Now, just recently, we've been doing quite a few tests on working platforms for piling rigs constructed out of our mechanically stabilized layer. We've been using the plate load test, but we've been using big plates. So why is it important to use a big plate when performing a plate load test on a working platform? Well, let's find out why. Brian, over to the flip chart, and I'll try to explain. So you have a ground level like that, a ground surface, and you have a plate load test. You all know what a plate load test, a circular plate that you put on the surface, you load it, and you measure the settlement. It can tell you the stiffness and the bearing capacity of this ground if you load it high enough. So the plates start off at about 0.3 meters or 1 foot diameter, but you can get bigger plates. Another common one, 0.6 meter diameter or 2 foot. Now, what difference does it make the size of the plate? Well, the depth of influence or the bulb of pressure is directly related to the diameter of the plate. So the depth here is up to about 2 times the plate diameter. So if you have a bigger plate, the depth of influence is going to be much greater. So even if this was all the same soil, you would still get a different result from this plate compared to this plate because you are testing a different volume of soil. And maybe the properties of the ground get different as you go deeper down. Now that becomes even more important with a working platform. Now you've got 2 layers. You've got the stronger working platform layer of compacted granular material. That's the working platform. And then underneath that, you have the softer subgrade. So now the bigger plate is influenced by this softer, weaker material. So we'll definitely get a softer, weaker response with this plate compared to this plate, which is only affected by the higher quality working platform material. That is important for working platforms because imagine we have a piling rig, for example, that is going to use this working platform, and that has a track width, say, 0.7 meters. What will be the depth of influence of that track? It will be similar to this large plate here. So clearly, to verify the design of this working platform and that it is safe to support the piling rig, you need to do a test with a plate that has a size, a diameter that is as close as possible to the track width so that the depth of influence is the same. So that if you loaded this to bearing capacity and verified the bearing capacity, you know you have sufficient bearing capacity for that plant there. That small plate is clearly inadequate to verify the design of the working platform because it does not have the correct depth of influence. This could be used as a quality control test just to check whether the granular layer is as was assumed in the design and has been compacted according to the specifications. But for verifying the design and the safety of the working platform, clearly you need to have a plate size as close as possible.
I think that's we can skip the remainder of that, but that was the bottom line I wanted to make, is that you should be using a plate load test of the right diameter so that you know what you're trying to study, right? Standard is 30 inch, no, 300 millimeter. Is it 1 foot? Yeah, 1 foot diameter is 300 millimeter, 30 centimeter. 30 centimeter diameter is the standard one. And then for airfield pavements, you have different criteria. There you can go to 30 inches over there. It's too expensive. It's very, very time taking because you need to mobilize like a truck to have a, because it's your, so you have to have like a reaction frame basically. You have to, it takes quite a lot of time. It's not very quick, but when you are trying to do, airfield pavements and stuff, like this is an example. When I was a grad student, the Chicago O'Hare Airport was undergoing the modernization program back in 2004 and stuff, and they were doing these kind of testing. Those of you who are familiar with plate loading testing, what's the purpose of the stacking of the plates? Any idea? Say it again. Towards stress concentration, but it's a plate. Why can't you just use one plate? Say it again. It's, well, related. You are actually trying to avoid bending of the plates because we are trying to measure the deflections at the circumference, right? So the plate actually sometimes bends as well. So if you make it thicker, the bending stiffness actually increases and stuff. So it's actually to avoid errors and stuff. So how do you measure? There are different types of measurements. I don't know about the Indian standard, but the Army Corps of Engineers, they actually measure at 10 psi divided by the corresponding deflection at 10 psi. Okay, whereas the Portland Cement Association for concrete pavement design, I'll show it in a second, what they do is they do the pressure divided by a given deformation of 0.05 inches. So there are two ways to measure, right? One is fix the stress, target stress, then measure the corresponding deflection. Here they are fixing the deflection and measuring at the target, at the corresponding stress stuff. Which one it is, it doesn't really matter. You just need to know what you're trying to do. There are some corrections. This is a correction for bending of the plate that I like to show. So think about it this way. If you have seen a plate load test, you're measuring the deflection on the circumference, right? So if the plate bends, will you record a greater deflection or a lower deflection? Lower deflection, right? So your K will be artificially higher. So you have to do a correction where you are going from say 350 to something like 300. Where did this curve come from? Empirical, right? This is all based on experience. This is all based on data and stuff. But that's the kind of correction they do. They have another correction for saturation. We're not going to spend a lot of time on it because you're not going to use it as much. If you're doing a concrete pavement design for sub bases and stuff like cement treated sub base, you have K correction. You have granular sub base thickness, you have a K correction and stuff. So it's all taken care of when you're trying to say that what is your zone of influence and what is it affecting and stuff. Again, as I said, a lot of stuff we need to cover, so I'm going to move on. Limitations: not easy to conduct, time consuming, needs a large reaction frame. Again, not a fundamental property. It is dependent on a lot of other things: plate diameter, saturation, and you have to really know that there is no plate bending happening and stuff. And okay, and one more thing I wanted to highlight here is another very common approach is relating resilient modulus to modulus of subgrade reaction. There is a factor of 19.4 actually they use. Okay, there is a reason why I actually had slides, but I deleted it because we don't have time for to all of that. Let me ask you this: when you are measuring modulus of subgrade reaction, like when you're measuring K, are you measuring elastic or plastic? Is it plastic? Is it 100% plastic? Or do you actually know how much is it elastic and how much is plastic? You don't know. It's a combination of both. There is plastic for sure, there is no doubt about it, but there is actually some elastic happening as well, right? But resilient modulus, when we go into that, and I'm assuming you know this already, is it's 100% elastic. You're talking about elastic behavior, right? So you are running a test where you are measuring even plastic deformation, and you are using that to predict only elastic properties, which is resilient modulus, right? So that's the challenge. That's the main lacking of that. There is another thing called automated plate load test, which is these days getting very popular. It's actually a field rig that was designed, and they actually do a repeated plate load testing to do what is known as in place resilient modulus measurements for layers and stuff. It's a very modern approach, modern thing. I just wanted to give you a glimpse of that and then pretty much stay there. I mean, I'm not going to go into that, but it's a way to measure resilient modulus of layers in the field. It's a lot of state DOTs like Minnesota, Iowa and stuff, they're utilizing this quite a bit. This David White, he was a professor at Iowa State before he became a private consultant, and Pavana Venapusa, he's actually from India. He's a Telugu guy. He was his PhD student and then postdoc, and then he's their lead technical person and stuff. So that's plate load test for you. Just an overview. You get modulus of subgrade reaction. You try to link it with resilient modulus. There are disadvantages, but it's still used. It's practice and stuff. So we finished CBR. We finished beam or stabilometer, and now we finished plate load test. Now we go into triaxial. Okay. We'll go for 15 more minutes. We'll take a break and then come back again. This is going to take us some time. Okay. Triaxial testing, and this is where spend some time because when I go to block 4, which or the repeated loading, we're going to rely on this quite a bit. So I want to make sure that we're all on the same page. So we're talking about cylindrical triaxial, and you know that why it is cylinder, we talked about it. So we have a chamber. Inside the chamber we have some kind of a confining fluid or water, right? You've used that and stuff, and when you apply some kind of a confining pressure to this chamber, it's Pascal's law. It is normal in all directions. It is hydrostatic. It is equal in all directions and stuff like that. So what happens is it's something like a sigma c is the confining pressure that you apply. So if you at the very initial stages, you have all of these are sigma c, right? And then you have a mechanically applied deviator stress. Those of you okay, let's do a quick show of hands here, and please be very honest with me. How many of you are being exposed to triaxial testing for the very first time? 1, 2. Have you seen triaxial before? 3, 4, okay, 5, okay. So triaxial testing is done inside a chamber, and then you fill a sample. So it can be it is usually a cylindrical sample. It can be, if you're working with the soils, fine soils, you can have diameters in the range of like 2.8 inches, 4 inches, 6 inches. This is inches diameter, up to 12 inches is what I have tested in my lab. So it's 12 by 24, which is like 300 millimeter diameter, 600 millimeter samples. So this is railroad ballast and stuff like that. So you're pressurizing the system, and you're applying what is known as confining pressure, and then you apply what is known as the mechanically induced deviator stress, and we call it deviator because that is what is the deviation from its standard state. When the truck goes, when a train goes, when an aircraft goes, that's where the load is, right? So basically in the vertical direction, sigma V, then you call it sigma C plus sigma D, and sigma H. There is a reason I write it as H. I'll tell you. You'll realize when we go into resilient modulus in next couple of days, it stays as sigma C, right? And what I was saying is, because in the vertical, and we agreed that because there is no shear here, these are all principal stresses. So this becomes your major principal stress, which is sigma 1. This becomes your minor principal stress, which becomes sigma 3. And in this case, because we are talking about a cylindrical specimen, sigma 2 and sigma 3 are the same, is the same, right? So now what you can do is you are going to apply the deviator stress at a given rate, and then you are going to punch, or not punch, you are going to deform induce axial deformation in the specimen, and then at one point you're going to have some kind of a shear failure, right? Because soils, aggregates, they always fail in shear. Even if you induce them, again, master students, PhD students and stuff, even if you induce compressive loading into these things, you are actually failing in shear. So that is the reason you measure shear strength and stuff, right? So imagine this is, let's go into a more circle kind of a frame, sigma versus tau, right? At the very initial stage, I have not applied any sigma d. I haven't applied any sigma d. How does my Mohr circle look? A point, right? Because it's a point. It's just a point. It's hydrostatic. It's the same stress under exact same. So this is what your sigma c is, and then you increase a little bit, 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 increase a little bit, increase a little bit. At one point, it's going to touch what is known as the failure envelope, right? What is a failure envelope? Why do we call it an envelope? Because it envelopes, it contains everything underneath. There is nothing above it. There is a stress state here, cannot exist, right? It's a failure envelope, right? What is the most common one that we use? What is this called? What kind of more failure envelope? Mohr Coulomb, right? C plus sigma tangent of phi, right? C is the cohesion. I like to call it apparent cohesion because not all materials have cohesion, right? But so that's the reason there is a linear. So a little bit of additional information for you. The Mohr Coulomb envelope is actually non in nature, but you are actually doing a linear interpretation, and that is the reason you always, a lot of times you have the C or an interpretation C. So you just have to remember that it's not truly linear, it's a non-linear envelope. Okay. Now this is sigma 3, this is sigma 1, that's the major principal stress, minor stress and stuff. At the second stage, when I do another test, what will happen? This is, let's just say this is 5 psi. Now I'm going to increase the confining pressure to 10 psi. Start this test at 10 here. So what will happen? The circles will get bigger, right? Because as sigma increases, your tau also increases. That's frictional behavior, right? That's frictional behavior. What if it is no friction? What if phi is equal to 0? How will the envelope look? This, right? When do you see this? Okay. Clay, pure clays, yes. You said something. Yes. When you have 100% saturation, then what you are trying to still work on the total stress and stuff. What will happen is all the stresses are actually taken by water. So when you are applying additional if you do it undrained, so when you apply additional loading, all of the loading is taken by water, so you're not gaining any strength. That's what happened, right? Though consolidated, undrained and stuff like that. Those, so you'll see those behaviors sometimes. So anyway, so now it's this get bigger. You have your the failure plane. You usually draw 3 and then draw a tangent. That's what we're going to do on in the tutorial today. You're going to see how this is done, right? And how you can determine this, how the data looks. That's what I have for you today. But the bottom line is you are going to use a more Coulomb failure envelope, which is going to give you so just do this, maybe like one circle here, one circle here, one circle here, and that's what a typical triaxial testing does, right? When you go into geotech, pure geotech, you can go into all the different forms like unconsolidated, undrained, unconsolidated, consolidated, undrained, consolidated, drained, unconfined compression and stuff like that. One more thing that is very relevant to us in pavement side of things is unconfined compressive strength, right? What is that? What does that mean? How does the Mohr circle look when I do a unconfined compressive strength? Sigma 3 is 0, right? Sigma 3 is 0. So this is called unconfined compressive strength. This is basically this is the compressive, no wait. This is known as the compressive, right? And then you have the double, the radius is basically half of that and stuff like that. That's how it works, right? So why did I go through all of this? Is we're going to talk about both strength and modulus using triaxial testing. Okay. Now, is everybody familiar with what is a strain controlled test versus what is a stress controlled test? Yes, I see some yes, some no's. Okay, so let's do a very quick review on that. How do you, let's think about a machine that you are running now, and you are going to say that I want you to apply 5 Newton of force on this table. How does the machine know that? How does it do? Have you ever thought about it? Yeah, but what is calibration? I mean, what's the science behind it? In crude language. I don't need exact science. Crude language. What is happening in there? Say again? No. That's the, I mean, we're not doing any free fall or anything. I'm talking. I have an actuator. I'm trying to push a piston. I'm trying to push. Yes, measuring the resistance. But how is the 5 set? No, why? Why is 5 related? That's a very good point. We'll get to that when we go into modulus and stiffness, but that's not necessarily true. So what he just said, it's very important, is that he's saying that I am applying 5. If I am stable here, then I am 5. I can apply. If not, then I cannot apply the force. Right? Can you push my hand? Apply some force. Push. Push. How much force are you applying? Now push. Right? So what is that? This is sample. This is my sample. Right? So if my sample is going to resist, then only my load is going to be valid. Otherwise, load is 0 if the sample is moving. But that's we still haven't gone there. That's an important point. We'll get to that in a second, maybe tomorrow or something. But how is a machine applying the load? There's something called a feedback loop. Right? It's a feedback loop, feedback system. Imagine you are saying that, imagine you are hanging a photo frame in your wall and you have your sibling or whatever, your friend or whoever standing behind, saying that, okay, let me know when it is straight. First they say, go a little bit right, and then say, no, too much right, go back, then go back left and stuff like that, right? That's feedback for you. You have a sensor in your loading system. When you are applying a load control test, you have what is known as a load cell here, right? The load cell continuously keeps measuring the load that it is feeling, and then it keeps sending back to your computer saying that this is what I am feeling. So when I am applying, my target stress is, say, when we go into resilient modulus, you will see this. When my target stress is 10 psi, the load cell keeps measuring it, or the pressure cell keeps measuring it, saying that no, I'm at 3, go up. So then you go up to 7, like no, still keep going up. Then you go to 13, it's like no, too much, go back, 10. This keeps happening at 1,000 times per second and stuff, at a very, very hard, fast rate, right? So that's called feedback. Okay, and the thing that governs that is something called PID, proportional, inverse, and derivative gain. We are not going to go into that. That's an equipment stuff, design stuff, right? So a stress controlled test in the real world honestly does not exist, because a machine only has control over what? The deformation. Machine does not control the force. What is the force dependent on? Your sample. I just showed you when he was trying to push my hand, I moved, so the thing was moving, right? So the machine actually is just saying, even if it is a stress control test, it is saying that I'm going to apply 0.1 millimeter of deformation, and let's see how much force I'm feeling. If it is not 100, if it is 2000, it's like, oh wow, this is way too much, I need to go 1/10 of that and stuff. So a machine is nothing, it doesn't know anything other than applying deformation, right? But the test can be, a triaxial test is deformation controlled or strain controlled. You say that I'm going to apply 1% strain per minute, and then I will just keep pushing this sample. Whereas when we go into modulus testing, you will see that I'm going to apply a 10 psi load pulse every 0.1 seconds and stuff. So because it's all triaxial, I wanted to give you this background on what is load stress control versus what is strain control. So just remember that. What is it are you asking the system to do, right? In triaxial testing, you are or shear strength testing, it's called monotonic triaxial testing, because monotonic means you are just pushing it at one given rate. Okay. Other than that, resilient modulus and stuff, when we get into that, it's going to be called repeated triaxial testing, because you're going to pulse it. That makes sense? There is another term a lot of times people use. They call it dynamic triaxial testing. Okay? That actually is probably the last thing we're going to say before we break for a little tea break. I'm going to highlight one little thing to you folks, and again, this is all going to build up on each other, so it's going to be relevant for you. When people say something like, I am determining dynamic properties using resilient modulus testing and stuff, right? Let's go back to our basic equation. What is F? Who can tell me K times X plus, tell me the other two terms. C X dot plus right, spring constant, the deformation term, the damping factor multiplied the velocity, the rate dependent term, and then the inertia term, right? This is a truly dynamic system. If you are analyzing a test data in the real dynamic thing, then you have to consider the inertia effects, you have to consider damping effects. In resilient modulus testing, whenever we go into that, you will see we are kind of still simplifying it only to the first term. It is a repeated loading test, but we are not doing a true dynamic characterization. So it's not a dynamic property. Modulus testing is not dynamic. Okay, because you are not considering the effects of damping, rate dependency, the inertia, and stuff like that. So triaxial testing, what you from here saw, is you can use it for shear strength, you can use it for modulus, and we can also use it on permanent deformation behavior. Let's take 2 more minutes to take care of that. Epsilon sigma, right? Static monotonic triaxial testing, shear strength. How does it look? Something like that, right? You have seen this many times, right? How would a repeated load testing look? You are applying something and then you are removing that. How would that look? You go up and then you come back. Where do you go back? To 0? Why not? It's going to have some plastic deformation, right? Next cycle, come back, come, do many cycles. At one point, you go into what is known as a hysteretic behavior. There is no further permanent deformation accumulation. That elastic stage is what we are going to talk about, is a resilient modulus and resilient stage. So is resilient modulus an elastic modulus? Yes, but after certain amount of plastic deformation has happened, and also it is something called a secant modulus, not an elastic modulus. We'll get into that. So why I showed you this is all this behavior from now on pretty much until the next 1.5 days and stuff, it's all going to be based on triaxial testing and triaxial behavior. Good? All right, take a break, 15-minute break, and then we'll come back. All right. Thanks, folks. Okay, let's get started. Still have a lot to cover. So we are in triaxial testing still, just basic components here. The whole system is in a chamber, and that's what applies the pressures. Uh, the loading can be either pneumatic or servo hydraulic. Very recently, there is another um, loading system that's called electric based systems that I don't know that much about, but I have seen those. And we have the feedback control, and we are going to simulate in situ stress conditions on soil elements and stuff. So couple of questions for you to remember or pay attention to is, we said that we also do what is known as unconfined compressive strength test for subgrade, pavement subgrades, right? And unconfined compressive strength is when there is no confinement. But if you are under inside a layer, right, like let's just say this is a geotechnical engineering concept and stuff, and you're talking about a soil element here, the confining stress is because of the surcharge, right, the upper load. And what is that? You geotech folks, do you remember sigma h prime is equal to what? How do you go to from vertical to horizontal? K naught, right? Coefficient of coefficient of lateral earth pressure. So you do that, right? So the question is, why is unconfined compressive strength test still representative of what you are trying to do? And the best way to illustrate that is actually safa kalar ko bhi pura safa hone na. Is there a wet like just way to clean this or something? Otherwise it's just very difficult to see. Khali wipe kar le ho. Let us take a very simple pavement system, and you all will help me calculate some stresses. Okay, I'm going to put like a 4-inch, and my apologies for US units, because that's how I teach, and it's much easier for me to convert numbers in my mind. And then this is hot mix asphalt, 4-inch, this is aggregate base, 12 inches, and we're going to put a subgrade here. Okay, and we are going to calculate, is unconfined compressive strength test representative of us trying to characterize this subgrade. Okay, so let's just take, so the gamma for HMA is typically 150 PCF. PCF stands for pounds per cubic feet. Okay, and for base I'm going to make it something like 100 and let's do 12 inches. Let's just make it say 135 PCF. A well compacted aggregate base will do that, right? So let's do this quickly, folks. Total stress, we're going to ignore pore water pressure. So total stress is equal to effective stress essentially in this case, right? So total stress, vertical stress on top here. Spray kar do. No, gote kaam kar chhadi ki poda. Manjire manjire use karibi na hole hote. Barambar na loss without. सब मिटा दिया. Girl. Sure, thanks. Okay, so 4-inch, 12-inch subgrade, we said 150 PCF, 135 PCF, and HMA and base, right. So let's do this. So sigma is equal to summation of gamma times H. I'm assuming everybody knows this already, right? Basic stuff. So 4 inches is what? This is PCF, right? So 4 over 12 multiplied by 150, right? Plus 12 over 12 multiplied by 135. So this is what? 3. So this is 50. This is 185. What? PSF, right? Pounds per square foot. We're going to make it into pounds per square inch. What do you divide by? Square of 144. So 185 divided by 144. Give me the number. .28 psi is the vertical stress on top of the subgrade because of the surcharge, right? What is a typical K0 value? Give me a typical K0. 0.33, 1 over 3. Very good number, right? Sigma H prime. By the way, I should not do it by sigma because it's kind of wrong because it's effective stress, but I'm ignoring pore water pressure. So sigma H prime is 1.28, 0.33 is equal to basically you're dividing by 3, so it's about 0.42 something, right? 0.42 psi is the horizontal confining pressure that this soil is experiencing because of its surcharge. Don't you think it's reasonable to just ignore it? Right? So that is the reason your soil is under so little confining pressure underneath the surcharge of a pavement. That's the reason you are kind of running an unconfined compressive strength is representative, because it's very low confining, right? So whatever you are feeling is based on the deviator stress. That makes sense? So shear strength, tau max. Sorry for the font, it's a little Mac versus Windows problem we always have. And this I have already shown you about sigma C, and sigma vertical is sigma C plus sigma D, and then you have a load distribution and stuff like that, right? That's should be straightforward. Again the same thing, but the shear plane you have a 45 over phi over 2, that's the inclination, and then that's where the failure occurs. Again, typical geotech stuff. You have multiple tests you are running, you actually get different curves, and then you are going to try to quantify as the confining stress increases, but one is unconfined versus that confining. The way I teach it in my undergrad classes, you all are above that, but the way I teach it is, you imagine a bunch of marbles and then take a this is interesting. How did I do that? This even requires talent for me to do. How did I manage to do that? Okay, I'll try to write with this. We'll see. All right. You imagine a bunch of marbles. You take a, do you know what a saran wrap is? Like a sandwich wrap, like the clear wraps that you wrap food in, right? Take one layer of wrap around that marbles, and then you try to put some weight on it. After some weight, it's going to collapse. Now take an entire roll of that wrap and then wrap it around. Then you're going to be able to stand on it. That's confining for aggregates and stuff. That is what it does. Once it is held together, because the particles don't crush, you actually have immense amount of strength, right? So that is the reason confining will increase your shear strength a lot of times, as long as it is being translated into interparticle contact. If it is saturated, if it is undrained condition, if water is taking all the load, soil does not care, right? That's what happens. You saw this. We're going to do this in the tutorial today. Okay, this is sigma versus tau, right? This is how we plot your more circle, and then you draw a tangent. A little step back, you have also seen probably in your life what is a direct shear test, right? Right? What is a direct shear test? It's basically some kind of a block kind of thing. It's a square thing. You are shearing it on top of each other. What's the primary disadvantage of a direct shear test? Predefined failure plane. When is a direct shear test very useful? Sand, yeah, okay, but let's talk about even clay soils and stuff. What situation you can really easily simulate using a direct shear test? When you are analyzing, doing a forensic investigation of a slope failure or something, you can actually collect samples there because it does already have a predefined failure plane. You can actually test the strength along that, right? So it's very straightforward. But why I am trying to ask you that is because your shear strength tests or direct shear, you have sigma and you have tau, and you get the points directly, right? You know that. You join that. That's your C versus phi, C phi. Whereas for triaxial, you have to draw more circles and you have to draw the tangent and stuff, and then you go. The point is, when you draw sigma 3 and sigma 1, so every triaxial test has a combination of a sigma 3 and a sigma 1, right? I actually try to call it not really sigma 1, sometimes I actually call it sigma 1f because it is touching the failure plane, so I call it sigma 1 at failure, not just any random sigma 1, because this is also a sigma 3 over sigma 1, right? It's not a failure condition, it's not touching you, it's not defining the boundary and stuff. So what you can do, I should have this, I don't know why I'm walking. What you can do is, this is actually what you will utilize in the tutorial today as well. If you just plot sigma 3 versus sigma 1 at failure for each test, and then you fit a straight line with that of the form of a plus b sigma 3, which is basically y equal to mx plus c or mx plus b, whatever. I think, do we still learn in this country mx plus c? Because in America it is mx plus b. So I have to change how I teach there. So I learned it mx plus c, and when I started like, where did c come from? I was like, okay, it's mx plus b. But sigma 1 is equal to a plus b sigma 3. So this a and b are not the same as tau is equal to c plus sigma tan phi, right? And this is sigma. So this is actually some work that was done long back, and I have honestly not been able to track the source. I think it's from Purdue University, but they actually did this, and they were able to say that for any triaxial test, if you plot sigma 3 and sigma 1 and plot this kind of a line, then your relationship is cohesion is a over 2 square root of b, and sine of phi is b minus 1 over b plus 1. It actually works out like that, and when we analyze this afternoon, you will see you can actually do that and to give you the failure plane. It's very simple. It actually works like magic. Okay, so you can actually do this plot and stuff, and then this is effect of maximum grain size on shear strength. When you have Dmax increases, again remember we are all talking about interparticle contacts here, how that gives you strength and stuff. So bigger contacts gives you bigger shear strength. This is your unconfined compressive strength. I've shown you this. Of course, you cannot run this on sand or anything because there is no unconfined strength, but you can do it on stabilized soils, clays and stuff like that. You can do that. This is just some examples on how moisture content and dry density actually affect that. So moisture content is 23%, 26%, 28.5%, 30.5%. Your biggest enemy for soils is water. Just live with it, right? No matter what you do to compact, no matter what you do, water is going to ruin you, right? That's just one of the things. So this is just one example. This is a device that, you know, basically I had a love-hate relationship with during my PhD. Throughout the 4-5 years of my PhD, I ran 216 shear strength tests on this one, and that was part of my dissertation and stuff like that. It was all assembled by hand and stuff. As you can see, it's not any vendor made. This was actually made by Professor Marshall Thompson long back, and this is one of the things. This is just my device from back then. But they actually developed something. This is another thing Professor Thompson developed. It's called University of Illinois Rapid Shear Strength, and there is a reason for that. When you are trying to do triaxial testing, if you go to typical geotechnical triaxial tests, the strain rates are extremely slow, right? If you're doing a drain test thing, you're really slow, right? And sometimes it can become prohibitively slow depending on what you're trying to get and stuff. So for rapid base and subgrade characterization, he actually came up with this method, which is 1.5 inch, which comes out to be 12.5% strain per second. A typical rate you will see is about 1% per minute. I'm talking about 12.5% per second. So this test literally takes 1.5 seconds to run once you assemble, right? But the good news is this is from some aggregate based materials. If a slow monotonic test 1% per minute, you got about 57.6 and 6.8. Here you are getting about 61.7 and 19.2. So very close in friction numbers and stuff. So for aggregates, when drainage is pretty much guaranteed, where excess pore water pressure and everything is not a problem, you can actually increase the shear strain rate and still get by with quite comfortably. And this helps a lot. Otherwise, you know, the number of testing will actually be very limited for you. This is another very important thing for us to keep track when we go forward, and I'm going to show this to you in a couple of different ways. When there is a moving wheel load, right? So let's take a look at how a soil element feels it. This is the road, this is a soil element, and I am sitting at the soil element with a pressure sensor and my watch, or I just, you know, have a data acquisition system. So the truck is coming from somewhere here, this way. With time, right? This is time, this is sigma. With time, for some time it is 0, 0, 0, 0, 0. It starts feeling something. It goes and disappears, right? As that wheel moves. This is called a load pulse. That's called a load pulse. It has a definite duration, it has a definite magnitude. And as you can imagine, intuition says that what will happen if I plot for here? How will the pulse look? What will it look like? Shorter or taller? Taller. Wider or narrower? Narrower. So narrow but tall. You know that, right? So, but there is actually another thing that's happening here as well. In triaxial testing, we are always aligning the sample like this, and we are loading this way and confining this way and stuff. The problem is when the wheel is over here at one point, this thing is not just experiencing vertical load. it has components this way as well, right? So it has horizontal components, it has shear components. Triaxial testing, conventional, what is the magnitude of shear? That's why we do principal stress analysis and stuff like that, right? So this is how an actual element feels. So if you plot the stress pulses, you have a sigma V, the orange one, or yellow, or whatever that color is. Then you have the sigma H, right? And then you have a tau, and the tau of course is 0 when you are directly on top of it. That's the principal condition. But look at these points, folks, these regions. What does it represent? Horizontal is more than vertical. What does that mean? It's pushing this way more than it is pushing this way. So your sample is extending, which is not something that you are simulating in your traditional conventional thing, right? Let me draw one more thing for you so that we all, so this is the chamber and this is the sample and this is sigma H and this is sigma V, because sigma V has a deviator component as well, right? What is the relationship in here, mathematical relationship between sigma H and sigma D in terms of inequalities? In terms of inequalities, what always holds true here? Sigma V and sigma H. What should I write here? What is the inequality? There. Yes? Always. Can we simulate a case when sigma H is greater than sigma V in conventional triaxial testing? No. Right? But are we facing those situations? Right? So that's where we go into something called advanced triaxial testing. Again, something on Thursdays, maybe Wednesday afternoon or Thursday. I'll show you a setup, how that does, why it is important, wheel load simulation is important and stuff like that, right? So just a piece of, you know, trailer for you that this is something that's coming. So as the stress is coming, wheel is over here, right underneath. As it moves, the principal stress direction changes. It's not always vertical, right? The principal stress direction rotates under moving wheel load. So static simulation testing is very different from moving wheel load simulation and testing, right? So that's where permanent deformation and everything comes. Typical strength correlations, there are so many different strength values like CBR, there is beam stabilometer, there is DCP which we haven't gone into yet, there is Texas triaxial, there is, you know, there is unconfined compressive. People have developed empirical relations and stuff. Now how much you use it, again it all depends on what situation are you faced with, right? When my graduate student wants to do something for their thesis, I am going to say no, go run these tests. But when an undergrad student working on a, you know, senior design or capstone design kind of a project wants some kind of information, I was like, okay, use this correlation, move on, because that's not your main focus. So you just have to realize what we are trying to do. Okay, so that's the base, like surface stuff of triaxial testing in terms of background. We'll get into that a lot more on repeated and stuff. Now we'll go into non-destructive evaluation. Triaxial testing is in the lab, right? We have a sample. Where did we get the sample from? We either cored it or we are doing what is known as the reconstituted sample, recompacted sample, right? It's not in situ measurement. Now we are going to talk about in situ measurements, right, in place. It's existing roads, most state projects, productive, repeatable, useful. We all know why in situ testing is needed. One of the most important or most common ones that we talk about in evaluation, pavement evaluation in general, is called falling weight deflectometer. Okay, how many of you have done some kind of stuff on falling weight, like coursework or research or something? Okay, all right. So what is a falling weight deflectometer? A falling weight deflectometer is basically a hammer that you drop on the road, or if you have a very well prepared construction platform, you can test it on there as well. And then you measure what happens to the surface around it. Okay, how do I introduce it in my undergrad class? I say, okay, in America, or well, a lot of you stay in hostels, so it's probably similar, right? In America, when students go to, you know, grad school or something, there is no hostel, right? They have to live in apartments, and the apartments, you have to buy very cheap furniture because you're poor. Every student is poor, right? So when you buy very cheap furniture, you have really bad mattresses, gadda, right? When you stand on that gadda, you basically sink, right? Versus you watch these TV commercials, is like, oh, you can do whatever you want and you're not going to wake up your partner, blah blah blah. Remember that, right? So that's what road is basically. A very crappy road, when you load, it's going to sink. A very good road, it's going to distribute the deflections evenly, and it's going to have what is known as a wider deflection basin and stuff, right? So we won't talk about that. So falling weight deflectometer is a pulsed load application. It's an impulse loading which is applied by dropping a load, basically, that drops here, and then it applies some kind of a pulse, and then you measure, and then you know obviously that underneath the load the deflection is the maximum. As you go away, the load is going to be, the deflection is going to be small, 0. And this is symmetric. So if you have on the other side, it will look exactly the same, or should look exactly the same if the conditions are the same. So that is called the bowl, deflection bowl, or what is known as a deflection basin, right? And why does that happen, and why is that very relevant? Let's do a distribution comparison here. If you apply a stress load here, and we know the stresses kind of dissipate something like this. Let us just say these are the pavement layers. This is HMA. Let's just say this is base. If this is where the center point of the load is, at this point the deflection is called D0. 0 stands for zero offset, D stands for deflection, and this is the subgrade. What layers affect the deflection of this point? Say it again. All, right? Because this one, this one, this one. If I measure the deflection here, what layer is affecting the deflection here? Only the bottom, because the top is not feeling any stress here because the dissipation has happened. You use that concept when you are trying to calculate your modulus values for layers and stuff like that, which is called back calculation. We'll get into that in a second, right? The whole idea is, as you move away from the load application point, the layer that affects the proper deflection or the behavior is going down, 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 down. So that's FWD. What are the FWDs? What is advantage? It's fast, it's inexpensive, results are not affected by boundary conditions, reliable structural number. For pavement design, actually for pavement rehabilitation design, even AASHTO 1993 has a complete method for using FWD to calculate remaining structural life and stuff like that. So this is my example of graduate student mattress versus rich people mattress, right? Weak pavement, you're sinking into it. A strong pavement basically dissipates better, right? Smaller deflection, wider basin. Larger deflection, narrower basin. It's almost like a punching, it's almost like a failure happening, right? Strong pavements versus weak these are just some values. I'm going to skip this. There are many, a lot of research has gone into this for many decades for FWD testing, how to apply the load, because again, remember the load, if you have a steel plate and if you drop a weight on top of it, you are again doing something similar to what CBR does. You're basically punching it. So you have to have some kind of padded contact that dissipates the stresses properly, simulates more like a pressure and stuff. What is the pulse width as well? How much should the pulse be? There is a lot of research that goes into it that we don't have time for it. But this is how deflection is measured. Most FWDs use what is known as geophones. Geophones are what? Who knows? What sensors? They're not acceleration. What do? No, geophones don't measure deflection. Geophones give you deflection. Geophones measure velocity. So you have to single integrate them to get deflection. So there are two different types of sensors, right? There is another type of sensor that is based on LVDTs, and they don't call it LVDTs, they call it seismometers. There is a device called QAB that uses seismometer that gives you directly deflection. You know, this Dynatest and everything, they have what is known as geophones. Geophones are velocity sensors. So how do you go from velocity to deflection? You have to single integrate with time and stuff. There are accelerometer based sensors, but not in FWDs. They are based in LWDs and stuff. Okay, so this is how it goes. You basically lower it, you measure it, and then you try to apply a pulse, and this is how the deflection curve typically looks, and then you can then use that. Now there is a concept called back calculation. Now I need to explain what is back calculation, right? I can't teach you to drive in reverse direction unless I first teach you to drive forward, right? The point is, what is back calculation? So if you have a pavement, let's go back to our pavement analysis that we talked about yesterday. You're talking about, I'm going to make it a two-layer system, just easy, E1, E2, mu1, mu2, H1, H2, and then I'm going to apply a load over an area. I'm going to say P comma R. That will give me the stress and stuff like that, right? So P comma R side, and I'm interested in the deflection on the surface at any point. So deflection is a function of P comma PR combination, basically, comma you have layer 1 E1 mu1 H1 and E2 mu2 H2, right? That is deflection. That is your beam theory. Your delta is equal to PL cube over 48 EI or whatever you do, right? That's that. Simple stuff. When you are testing in the roadway, what do you know and what do you not know? Do you know H1? Hopefully, right? Hopefully. Let's just say yes. Do you know H2? Yes, probably, right? Nu1 and Nu2, probably, I mean, it's not very sensitive. So you have like typical ideas, like what's the Poisson's ratio of water? .5. Who said 1? I have a story for you. I was waiting, if somebody said 1, I'll tell you the story. And I will not name the professor. I was a student at IIT Kanpur in my 3rd year, 6th semester. And the professor asks, what is a, and I think some people can guess the professor's name. The professor asks, what is the Poisson's ratio of water? And I said 1. And the professor looked at me and he said, I want you to jump out of this window and I want you to have scars on your body for your entire life for saying that. And I was about to cry and stuff. But anyway, it's a joke. I'm not going to make you jump out of the window, but it's 0.5, right? So what is the Poisson's ratio for concrete? No, 0.35 is too high. That's asphalt. 0.15, 0.15, 0.35, 0.3 is close to asphalt. Soil is about aggregate is about 0.3, 0.35. Soil, subgrade soil, you usually take 0.4, something like that. So what I'm saying is Poisson's ratio is not very sensitive. You probably know this. Do you know P? Do you know R? Right? So what do you not know? E, right? So what you're going to do is you're going to back calculate the E. The forward calculation is when you have all the properties and you are trying to find deflection. Oh, by the way, in the field, do you know delta? Yes, because you're running an FWD test. You know the delta. So now you have delta and now you have all the others and you're going to try to back calculate the E. That's called falling weight deflectometer layer modulus back calculation. It's no rocket science. The mathematics there is probably a little complicated, but the concept is very simple. You don't have all the forward calculation properties, so you just are back calculating. How would you back calculate? What you usually would do is, I'm going to say, let's assume E1 is say 400,000 psi, E2 is say 40,000 psi, and I am going to plot, this is going to be distance, so radial distance or offset, I'm going to call it offset, and I'm going to call this deflection, okay, and I'm going to say radial offset is 0, deflection is going to be very high, right? As it goes away, 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 deflection is going to go low, 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 right? So this is my predicted basin when I used 400,000 and 40,000, right? But then you go and run an FWD and you are like, my basin actually in the field looks like this. So what did I just do? I under predicted deflection. So I overestimated E. So I should be reducing the E somehow. So maybe I should make it 75, maybe make it 35, something, try to make another line. Then you have another one, you do have another one, ultimately you converge. It's not that straightforward, because if you change the two values together and stuff, you're going to be running and chasing your tail your entire life. You have to have a strategic one, and there are convergence algorithms where they actually do error is equal to delta measured minus delta predicted square summation for all the sensors and stuff, and you just do that, right? So that's back calculation. There are many softwares available. All of them, most of them have some kind of a layered elastic analysis program in the background, and then how they differ is the way they minimize errors and stuff. How's the error minimizing technique and stuff like that. There are several softwares available. A very common question is which is the best software to use. The very good answer is that the software that you know to use the best, right? It's not about which software, it's like how good you are to use whatever you're using, right? You can do the same thing, anything. What are the factors that are affecting load? Yes. Pavement factors, yes. There is layer properties, there is layer thicknesses and all of that. The climatic factors, right? You go in Bhubaneswar and you do in December testing versus you do in July or June mid testing, then your deflections are going to be very different, because asphalt is a stress sensitive temperature dependent material, right? Or if you go to a cold place where freeze thaw happens, you test in December, January, the subgrade is pretty much frozen, your soil, your system looks amazing, but then you go in spring, it is thawed and stuff, it is full of water, it looks like trash. So you have to worry about climatic factors as well. Stress sensitivity, this is something we'll get into in the next couple of days and stuff. The problem with unbound materials is that they are not constant modulus, just like the saran. How many saran wraps you have, it really matters. If you have one layer of saran wrap, it's very weak, aggregate is. If you have multiple layers, it can be a beast, right? So whether you can, when you apply very low value of loading versus a very high value of loading, the behavior is going to change. So pavement factors, what is going to change? Distress. Can you tell me why distress is important? Why is distress important when you are doing FWD testing? You don't understand the question, or you're hungry? Either one is good answer. Exactly. Because the basin happens because of the load transfer and stuff, right? If there is a crack, the load may not transfer. You may actually think that, oh, it's really good pavement, but it's actually because of a crack, it didn't transfer, right? So it's very important. Transverse location, what is that? Where are you with respect to the joints and with respect to the shoulder, with respect to the boundary and stuff, right? Where you are applying. Surface discontinuity, which is similar stuff to joints and stuff. Subsurface variations. I was once working on for Idaho Transportation Department, they gave me some FWD data to help them analyze for some rehabilitation planning, and we had like I think 20 miles worth of data, and we were analyzing at one place. The numbers were just crazy. They were just like crazy. I mean, all of his sudden deflections were like almost like a step function and stuff. And I said, something going on here, go and take a look. And they were able to go and look. They actually saw a pipeline had burst over that location, underground pipeline, and it was completely flooded. And the FWD was just, you had not seen it on the surface, but it was really bad. Underlying voids, very, very relevant for concrete slabs and stuff. When there is erosion happening, washout pumping and stuff, you have really big deflections there and stuff. Random variability also affects. Typical deflection versus time plot. I have told you this a little bit. December, January, February, March, you will have really, really small deflections because this is for a typical North American soil where you have very harsh winter and stuff like that, right? So you have really harsh winter, the water is kind of frozen, subgrade is very strong, but in April it starts thawing. April and May you have really, really bad deflections, and then it starts reducing as well. Yes, in June and July, maybe in the summer the asphalt is probably giving higher deflection, but now the soil has dried up, so it's kind of counterbalancing each other and stuff. So some of that happens, right? So you have to have temperature measurements, you have to have air and pavement, you have to have corrections, you have to compare everything to a standard temperature, otherwise there is no comparison, right? You have to do temperature corrections and stuff like that. 30 to 150 meter intervals, outer lane only. Why outer lane only? What happens on the outer lane? Trucks.
Yeah, trucks primarily go on the outer lane if they are following traffic rules, right? But that's kind of, you have to make some assumptions. Both directions you have to have staggered, flexible outer wheel path, JPCP, JRCP, mid slab, joint, corner, because of the deflection patterns are different and stuff. You have to choose where you test. CRCP, it's basically outer wheel path. Interpretation, I'm going to skip this. How do you interpret FWD data? Now this is very important, folks. You all are pursuing some kind of higher studies or something like that, and you are in research right now, and then when you go and you are like, okay, give me a back calculation software, what is it's called, what, IIT back or something, KGP back. So is that still used commonly? Nice. So you are like, okay, give me KGP back, I'm going to be able to use this and stuff like that. The point is, on a daily life for an application or for a practitioner, back calculation is not a very trivial thing, right? A lot of times they look for simpler solutions, right? So there have been a lot of simpler solutions, and you read Professor Thompson's paper last night, and there is one place he clearly mentions that the solutions should be only as complicated as long as they're implementable and stuff like that. Otherwise, it just goes away. So one thing that they do is the deflection basin, they have determined little parameters. This area parameter is not truly a area. I mean, I used to think when I was first exposed to it, I used to think this is the trapezoid area, so it's basically sum of the two parallel sides plus multiplied by height, but it's not. I checked that and stuff. It's a little bit different, but the point is, you see the relationship here, folks. You can set up a very simple Excel spreadsheet to do this. You don't need back calculation, forward calculation, multi-layered elastic programs and stuff like that, right? So what they did is they kind of defined this and said that higher area is basically higher, better structural integrity because it's spreading over a larger width rather than being a sinking thing. That's why you are normalizing with respect to D0 or D1, whatever you want to call it. Then there is another thing called area under pavement profile, or AUPP. What they did is they drew like a rectangle from D0, and then they said this is the deflection. Now I'm going to track AUPP, like whatever is remaining between this deflection and stuff. And then they were able to link that to asphalt modulus, which is log E multiplied by T cube, which is a thickness cube, epsilon AC, which is the lateral strain or horizontal strain in the asphalt layer and stuff. So this is all done mechanistically, and then try to calculate, saying that if this is what your area or your FWD data is giving you, then you should be able to get some idea about what is the strain, what is the modulus and stuff like that, without running full-fledged back calculation. I am not saying this is a replacement for back calculation. I am saying this is a easier way of implementation, right? So one of the best things I like about this approach, and the whole thing that Illinois did and Professor Thompson did, is his work. I mean, when we get introduced to IIIPAVE on Thursday, you will see that IIIPAVE is one of the first finite element based softwares that took care of stress sensitivity of granular layers and subgrades and stuff to calculate pavement response. But what he did is he did all the research in the background, and almost like what you are doing these days, like this machine learning and artificial intelligence, like the big data kind of thing. So he would actually run thousands and thousands of analysis in the background, and he would actually develop typical trends and curves that if your values are like this, this is how it is and stuff. And he would give those values or those curves to the DOT personnel, saying that just use this. Now, if as a researcher later on, when you track this, like, okay, what is the source of this? Then you go back, you're like, man, this is all based on extremely heavy finite element coding and modeling and stuff. But the practitioner is not being bogged down with all of that. They are just having curves or simple equations like this. Like this fatigue equation is probably based on, I don't know, I'm just getting maybe 250 FWD analysis or something like that, or even more than that. It's just in the background. So, but the bottom line is, this is still valid for the areas that they considered. Structural coefficients A1, A2, A3, probably you remember from ASTRO 1993, that's the values, so you can actually link them and stuff. ASTO, it actually tells you about how to determine the MR. It actually says, you know, at what distance you are going to get only the subgrade. See this, 24 to 48 inch, that's basically what I wiped over there. So when you have the, man, this marker is falling apart. So it's this. So when you are at least 48 inches apart, away from the load center, it is saying that you are only being affected by the subgrade. So you start from there, and then you keep moving back. Stuff. Back calculation is an ill-posed inverse problem. What does this mean? Do you realize it's an inverse problem, right? What is the ill-posed means? Yeah, it doesn't have a unique solution, because technically you can find E1, E2, E3, E4 combinations, different sets that will lead to the different same basin and stuff. Technically. Practically, will it happen? I haven't seen many times. You still have some certain, you know, values and stuff, but it is actually an ill-posed inverse problem. Again, back calculation programs, ELIBAC, EverCalc, LMOD, BoostDef, ModComp, WestDef, ComDef, blah blah blah, FA back, all of them, they are all available. Modulus is something that I have used most, and to some extent LMOD. But again, I can guarantee you, as long as you know which one you're using properly, you'll get good answers, you'll get good results. You just have to become an expert on this. This is something I already drew for you, calculated versus actual field. Then you start mixing, then you start moving, ultimately you match. That's basically the purpose of back calculation. Iterative scheme in back calculation programs, I think you know this already. We have taught FWD deflection. So you have load, sensor spacing, seed modulus, layer thickness. You're going to do something like a chevron N layer, or your IIT PAVE, or, you know, min layer, whatever you're going to use. You found a compute theoretical deflections, and then compare that to the FWD deflections. Is it under tolerance? Yes, then you're good. No, change modulus, go back. That's what happens programmatically and stuff. And you can, with the modern programming abilities and stuff, you can write your own. And on the last day, I'll actually show you some open source resources that you have. Like actually, I had a much junior, but I had a colleague at University of Illinois who is really big into open source programming. He has actually developed his own Python based layered elastic analysis program that is open source. It's actually available for anybody. So I actually use it in my class. I give it to students. I tell them to play with it and generate multiple things and stuff. So it's, you can just take that, you do it as the forward engine, you have some kind of an error minimization, you have your own back calculation program. Right? These days it's very, very simple. It's not that difficult. Okay, I don't think anything here. Again, Poisson's ratios, we have already talked about it. Poisson's ratios, these are the typical values. You don't really, when you do forward calculation, you will see Poisson's ratio changing, does change the numbers a little, but it's not very sensitive. So Poisson's ratio is something you can pretty much assume and go by. Typical modulus values. I don't know how you all do this, because but when I was a grad student, I was once taught this trick, and I always follow that till date. It's in English units, US customer units, but it's very easy. Just have to remember the number 4. If you take concrete, the modulus is 4 million psi. If it's asphalt, it's 400,000 psi. If it's aggregate, it's 40,000 psi. If it's subgrade, it's 4,000 psi. The representative number, you will get by with 90% of the cases. Subgrade 4,000 is a little bit on the lower side, but 4 million, 400,000, 40,000 are very, very good guesses for E values if you're doing pavement design and stuff. That's how I use it. Megapascals you can convert, 6.89. Predicted deflections, this is how it works. As I told you, iteration 1, percent difference is 20.5, 1724 was E1, that is the trial, and your delta was, these are the delta values, and then second, look here, what happened folks. Look, the E1 remains same, E2 remains same, E3 and E4 changes. You know why that happens? Remember what I said is at D0, what layers affect your properties? All of them. So if you want to match D0 to start with, you're going to be chasing your tail, right? So you have to start from away, only change E4, then only change E3, then go back to E2 and stuff. Start from the outside, makes life easier. So that's the reason from iteration 1 to 2, you don't see any E1, E2 change. Here also no E1, E2 change. Here you see a little bit of E2 change now coming. Then you go to E3, E1 change, and then finally you are at an average difference of 0.9%. Any questions? Does that make sense? What was doing here? It's just error minimization. Okay. E bottom is the function of deflection beyond 1 meter, effect of underlying rigid layers. You have to consider that. There is one thing that Dr. Sahu and I we were talking about is the back calc schemes work really well for conventional cases when as you go down the layer quality decreases. If all of a sudden you have a stabilized layer which is actually stronger than the layer above, it kind of goes crazy on you. So you have to have special tools, abilities or skills to address that and stuff. So this is again Illipave based log EAC modulus is, look here, this is what I was talking about. Look at the EAC, this is asphalt modulus. What are the inputs? D0, D1, area, temperature, D2, D3 and thickness. What does that mean? A DOT engineer running an FWD test in the field can calculate this on the spot using an Excel spreadsheet or something, or even a calculator if they're good, right? This is what we will play with on Thursday. It's called Illipave. It's a finite element based pavement analysis program that takes care of stress sensitive unbound aggregates and stuff, and you can actually use it for back calculation as well, not directly but iteratively, like you can predict, check and match and stuff. I'm going to skip this is not very relevant. Okay, couple of other things before I think we're doing good. What slide am I on? Okay, all right. So this is called light FWD or lightweight deflectometer. Okay, so what is a lightweight deflectometer? Like FWD is a vehicle basically. I mean it's a trailer pulled by a pickup or a van or a jeep or whatever you want to call it. It goes and stuff. Now if you have a subgrade construction happening, you're not going to get a vehicle on top of that. It's not possible, and it's not very portable. You probably have one in the state of Odisha or maybe more. I don't know. That's a common challenge, right? What lightweight deflectometer does, it's a portable device. You can carry it on your by yourself. You do the exact same thing. You apply a load, and then here on the plate there are sensors. There you have some accelerometer based sensors as well, which need to be double integrated, acceleration to velocity velocity to displacement. Some have velocity sensors, some have direct LVDTs or just direct displacement measurements. And then there is a load cell here in some models, some models also do not have any load cells here. Umesh, do you all have an LWD here? What brand is it? Dynatest. So, okay, so if it is a Dynatest, it has a load cell in it. There is another model from Germany called a Zorn, Z-O-R-N or Z-O-R-N. It does not have a load cell. There is a different theory to it and stuff. But here, you are only talking about central deflection. One. So, can you calculate different modulus for different layers? With one deflection, can you back calculate multiple layer modulus? No. It's a combination of everything. So what you calculate is something called E foundation or something. It's a composite modulus. There are abilities to extend it like this, offset sensors that you can do, and then some back calculation, but most of them have only one central deflection. You do it and then you measure. Okay, so there is a many German dynamic plate, TRL, Dynatest. I use one that's called Olsen. So in my group we have done a lot of work on LWDs over the past several years. This is usually very good. It's very portable. You have some idea quickly. Deflection, you get some kind of deflection. I have actually developed some compaction protocols that is used in practice for open graded aggregate compaction using LWDs and stuff, saying that, you know, test it, and if it is not less than 0.6 millimeter, go back and compact it again and stuff like that. So those specifications, it's used. I have developed this. Loadman, we're going to skip this. That's my advisor, by the way, from many years ago. This is during my PhD studies. This is a photo, actually. I mean, I took this photo. This is E. What I was trying to show here is there is one deflection. There is a stress distribution factor based on the plate rigidity, and then there is contact pressure, there is radius, and there is Poisson's ratio. But you're basically getting one E. You are not getting multiple E's. It's basically similar to Boussinesq theory and stuff. There is something called SASW, spectral analysis of surface waves, which is again a waveform analysis that is done. Very niche methods. You know, you have to be an expert in surface wave analysis and stuff to calculate modulus values of layers because of this. Basically, they measure the surface waves. Shear wave velocity is related to modulus, shear modulus and stuff, and that's how it goes. Okay, field testing. I think couple of things I wanted to show before we go. I'm going to primarily focus on DCP, dynamic cone penetrometer. I'm sure most of you have heard about it, what they are, how you can do that. One, we'll start with something called static cone penetrometer. I don't know if you have heard about it. It's basically you just hold this and you push it into ground, and then you get a resistance, and then you have some theories or some equations for that. This is the DCP. You have seen this. It's a 60-degree cone. You have a 8 kg hammer falling over a 575 millimeters, and then you drop it. You measure what is known as a penetration rate. The penetration rate is linked to some form of, say, shear strength and stuff. So CBR to DCP correlation is something that's very common. It was originally developed in South Africa, and it's portable, blah blah blah. This is how it looks. There is a measurement stick, and then you measure. This is a very common equation. I would show you some data this afternoon usage of this, how we calculate CBR using this and stuff. This is called the Klein equation in inch per blow to CBR and stuff. How many of you have run DCPs? How do you pull it out of the ground? You guys are all that strong? I sometimes on tough soils I have had so much trouble pulling this out. I wish I had something like this. This is a really interesting thing. This is when I was a grad student. This is my PhD project. This is in my group right now. This is like last year's study. So yeah, it keeps happening. Subgrade strength testing just with DCPs and characterization and trying to find the CBR and stuff like that using this. So this is Errol Tutumler. This is my PhD advisor. That's me. And this is an engineer from Illinois. This is what you would end up with by taking the penetration rate and analyzing DCP data. You can find like a CBR profile, and then you can take a, let's just say your area of interest was 6 inches or something. Then you can say, okay, over the first 6 inches, my CBR is on an average this much and stuff like that. That's how soil conditioning in the field happens when you're trying to build test sections or when you control water and stuff. We can do that. These are a lot of equations for connecting CBR to DCP depending on where you are. The Klein equation is what I use the most. It has worked very well for me and for all projects that I have been involved in. North Carolina DOT developed something, Norway, US Army Corps of Engineers, Israel, Livne, I think they are also, I don't know where they're from, but yeah. And then you have CBR. By the way, today when I go home, after you go, I will send you this document, Garcia Thompson. It's a PDF document that compares a lot of soil stiffness and strength evaluation methods and stuff. It's a very good read. It's again Professor Thompson and one of his ex-PhD students, Gabriel Garcia. I'll send you this. DCP CBR correlations, again how they compare. The Klein equation is right here, and then Webster is the black one. NCDOT is over here. It's kind of overestimating the CBR. All the others are kind of close to each other, as you can see. So you just pick one, whatever works, and that's how we have used. This is the one that this is my writing. Yeah, we use it all the time in my group and my PhD as well. Again, correlation chart. You have CBR, you have DCP penetration rate in inches per blow, millimeter per blow, cone index. This is from the static cone penetrometer, just pushing it and stuff. And this is also QU, unconfined compressive strength. Sometimes you have relationships with that as well to calculate CBR and whatnot. Clegg impact soil tester. Again, these are hardly ever you're going to come across. I just have them because these exist. CBR is Clegg impact value square. It's basically it's a QC tool that you drop something, you impact something, and an accelerometer measures small strains. Vane shear, I think some of you may have seen this, right? It's you insert it and you rotate it, and it basically a shear measurement, just quick measurement of soil quality or soil strength and stuff. This is a very, very important slide. Again, this is going to be in the same document that I have used many times when an undergrad student comes and says, I'm working on this project, can you tell me how I can do this? And I would just go and say, okay, you have uncompressive strength, then just go CBR is divided by 4.5. If you have cone index, go divide by 40 and stuff. Again, empirical, but what are you looking at? What is your objective? Are you doing research in this? Are you wanting to do? Yes, then no, this is not good. But if you're just trying to find a quick ballpark number and stuff, this is very good. Soil stiffness gauge, this is something that doesn't get used as much. I did it quite a bit in my PhD. It's a very small strain vibration that actually induced. So it's a very, it's like a little suitcase kind of thing that you just carry, put it on the soil, it just ground, you ensure good contact, and then you turn it on, and it applies 20 different frequencies of vibrations and measures the deformation, and then presents something called a stiffness and a modulus, both of it. It's good for near surface measurements. So for example, if you have a thin layer, like you have only like a 3-inch thick layer or something, then if you do an LWD or something, the influence bowl is going to go beyond that 3 inches and stuff. This gives you a good number and stuff. There's 10 kg weight, and it applies different frequencies, and then it just measures you modulus and stiffness. And see, a modulus of the top 0.1 to 0.2 meter, like 4 inches to 8 inches of a wide range of soils. Cannot measure on wet soil and hard paved surface. So not at all on a stable base or something. You're going to get garbage. It's just going to get vibrated. This is from my PhD work. Very small vibrations. This is the relationship it gives you Young's modulus and shear modulus and stuff. This is just some display we had in one of the projects. This is actually an interesting thing. Vane shear test, easy to use, yes. Clegg impact, yes. Light drop weight tester, yes. GeoGauge, yes. Experience in research, vane shear, yes, you have quite a bit. Clegg impact, not really. Light drop testers and GeoGauge, no. What do you measure? Vane shear measures shear strength. Clegg impact measures kind of CIV, and then you can correlate to CBR and MR. Lightweight drop tester, deflection modulus. Now this thing, it's old, but now it has changed quite a bit. There has been a lot of research. Assumes that max deflection is elastic. This is a very standard problem or standard assumption when you are applying even in FWD. When you are applying the pulse and you're measuring, is it all elastic or you already accumulated some plastic that is being accounted for that, right? So that's something. Static cone, dual mass, you can take a look at that. Testing versus traffic loading, load duration, load magnitude. Impact devices have a very, very high load magnitude, but small load duration. But GeoGauge or something, you have very, very small load magnitude. You're taking really, really small strain measurements, right? But you're measuring over a larger duration and whatnot. Again, this is during my PhD, a couple of graduate students helping me during my work. They're both professors. This is actually one of the, I'm going to show this, and I think we can probably end it here. This is a plot from my dissertation, and as you can see here, so there are 3 sections, okay? So all the closed circles and closed triangles or filled triangles are LWD, and all the open ones are GeoGauge, the vibration. So the same things being tested, 2 devices, okay? So section 1 is the black, and if you see here, the GeoGauge small strain usually gives larger modulus, that's why it's higher. Red, again higher but similar range, but 3, something happened and you actually saw LWD actually all over the place, but GeoGauge was very, very high, okay? So as you can see, like this similar range and this similar range. So we were like, what's going on? Why is the GeoGauge in this case is consistently high, whereas the LWD was bouncing around and stuff? So then we went back to take a look at this, and this is actually another thing. What you will see is the average CBR was 3, average CBR was 2.7, very close to 3, but this is actually about 3.9. So CBR was actually higher, so it's actually a stronger layer, okay? But LWD was not able to catch it. It was bouncing around because the layer thickness was also small, so it was also being affected by the subgrade, whereas the GeoGauge isolated it and said that okay, it's good. So this was one example where it actually worked better in identifying the cause of what was going on, significantly stronger than the other two sections. And this is what it was. And look here, section 3, even relative compaction was the highest, 96.2, but LWD modulus was not showing that, but GeoGauge modulus actually was actually tracking it because it was able to isolate, because it's in within the layer and stuff. So what are the problems? Subgrade evaluation, you have to have so much value, you have so many test results, right? Anywhere between 10 to 100. What is the representative value? Do you design for the worst condition? Do you design for the average condition? Do you design for a percentile or so? That depends on who you are working with, your specification and stuff like that, right? We are going to have engineering properties as a function of time, strength considerations, change in moisture, as built subgrade, soil type, local effects, which is drainage grade and stuff, swelling soils, frost action and stuff like that. And you have to sometimes DOTs would establish something like a typical value, which is CBR, unconfined compressive strength. I haven't gone into ERI yet intentionally. I'll show you that when we go into resilient modulus. It's related to modulus, breakpoint modulus. Again, some typical values. I don't think we need to go over any of this. What changes? This is a modulus. When 1% moisture increases and stuff, loam and silt had the highest percent change in modulus versus clay. Clay is very sensitive, but when you change 1% or something, it doesn't collapse like that, but silt would actually collapse a lot of times. So that's it. That's pretty much it. Right on time. Good planning, right? But yeah, so that's pretty much it for subgrade evaluation. What we are going to do is we're going to break for lunch. When we come back, I will show you some typical triaxial shear strength data. I'm going to share that with you. And then I will show you a spreadsheet how that was used to plot more circles and tangents, and you can get working. And I will also show you a MATLAB code that we developed in my group to automatically read the files and plot them and show. So it's going to be a good exercise. Oh, and we'll start with looking at your spreadsheet from yesterday if you finish that one. Okay, that's it. Thanks.